thanks for having me here today. I unfortunately don't have as exciting of a teaser as Michael had. That was pretty cool. So, as Eli said, I'm at Zlonis. I'm with Minnesota DNR. Our research unit going to be talking about wood duck nesting habitat today. But first, taking a step back, why would we even be interested in studying wood duck nesting habitat in Minnesota? Well, we should keep in mind that Minnesota is a very important place to wood ducks for breeding habitat. Here are some kind of broad scale predictions from the Upper Mississippi Great Lakes Joint Venture, and we can see that kind of the parts of the forested region and the transition region of Minnesota are predicted to be very important to nesting wood ducks. And in turn, we see that wood ducks are very important to the people of Minnesota. So one kind of obvious way we could measure that is through something like hunter harvest. And wood ducks are very consistently the second most commonly harvested waterfowl species in Minnesota, behind only the mallard. When we're talking about wood duck nesting habitat, really what we're talking about is natural cavities in trees. So this is not at all to say that nest boxes aren't an important tool for wood ducks. They certainly are, have been shown to be very important for boosting local populations. But at the broadest scale, the vast majority of wood ducks are nesting in natural cavities. So the best estimate that we have out there is that about 95% of the fall flight of wood ducks is actually hatched out of natural cavities. Despite this aspect of their breeding biology is relatively little studied in Minnesota. There's been a couple, what I would call somewhat local studies from the 1960s. So we're hoping to add some kind of oomph to the research behind what's been going on in Minnesota. And then finally, there's been this kind of common thread that we picked up on from talking to a whole bunch of different people, that we can likely influence the most positive change for wood ducks and other cavity nesting ducks by first understanding their use and availability of natural cavities, and then potentially using that information to influence forest management decisions. Which kind of leads me into our objectives, and we have a few primary objectives related to nesting habitat. Today I'm only going to have time to really dig into one of those, and that's to identify tree and stand level forest attributes, so things like diameter, breast height of trees, stand age, that might be related to the formation of cavities suitable for use by nesting wood ducks. And really the key management outcome here that we're hoping for is to provide more explicit quantitative data to forest and wildlife managers regarding when and where, so the types of trees and forests that are actually producing cavities that could be used by wood ducks. I did want to note, just as an aside, obviously from Michael's presentation and also the bat presentation earlier, there's a whole lot of other species that are using cavities. In terms of large-bodied secondary cavity users, there's also a smaller subset, but still quite a few. And some of the habitat or the cavity requirements for wood ducks very likely overlap with these species. So I think it's important to keep in mind that there could be some utility to this research to other species. Our study was conducted just west of here, mostly in the Chippewa National Forest. The outline box here is kind of northern Cass County. And it's, as I said, mostly Chippewa National Forest, although there's a lot of state and county land sprinkled throughout there, especially at the southern area of the study area. Pretty good place for wood ducks, probably not the highest breeding density in Minnesota, but an attractive place due to a high diversity of wetlands, from ephemeral ponds and beaver ponds, large lakes and rivers, wild rice marshes, things of that sort, and obviously just extensive forest habitat that provides cavities. For our sampling, I'm just going to talk about methods for a couple slides here. We wanted to key in on older deciduous stands. We know from other research that that's where most cavities are developing. So we randomly selected older deciduous stands, at least 50 years old, and randomly placed between 1 and 5 plots, depending on the size of the stand, where we would actually go and sample cavities on the ground. When we got to a plot, we set up a 20-meter radius where we measure all trees that were over 22 centimeters, which is about 9 inches, and this is the kind of smallest tree we could find in the literature that actually had a cavity that a wood duck used for nesting. So we wanted to get that whole continuum of trees that are actually potentially having cavities that could be used by wood ducks. For each tree, a couple simple attributes that will come up a bunch in this presentation: tree species, diameter, breast height, and health status. Health status was collected on a continuum from live healthy trees to live declining trees, which are showing some signs of decay, either through broken branches, dead branches, fungal growth, things of that sort. And then third category being dead trees, which obviously encompasses a pretty broad spectrum of structures. At each tree, we would search for potentially suitable cavities during leaf-off conditions. So this is mostly from late fall through early spring, just so we could have the highest detectability of any cavities that were up in the canopy. When we did find a potential cavity, we would inspect it with a camera system we had attached to a long retractable pole. We could get this up about 16 meters into the canopy of forest, insert it into a cavity, and then view a video feed on a tablet down on the ground and actually inspect the interiors and determine if the attributes were suitable for use for wood ducks. So at those cavities that we inspected, recorded how it formed. So was it excavated by a woodpecker or broken limb, something of that sort? How high off the ground was it? And then most importantly, its suitability for use by nesting wood ducks, which included some information we got from the literature, an entrance of at least 6 centimeters, depth of at least 10 centimeters from that entrance down to a potential nesting platform, then a nesting platform of at least 14 by 15 centimeters, which is just big enough for a hen wood duck to incubate or clutch. Jumping into results, we've sampled 323 of these plots in our 2 years of study from 164 stands across the study area, and measured about 8,000 individual trees of 27 different tree species. The 7 that I have listed here are the most common tree species and the ones that are going to kind of come up again a few more times in the presentation. Most common quaking aspen, then basswood, sugar maple, northern red oak, paper birch, red maple, and bigtooth aspen. In those 8,000 trees, we measured or inspected 1,200 different potential cavities. 223 of those, or about 19%, were deemed suitable for use by nesting wood ducks. So the vast majority, or 65% in this case, were not suitable for use by nesting wood ducks. These other 2 categories included unknown, which are cavities that were either too high for our camera system or had some obstruction, and then in addition to that, marginal cavities, which are cavities that were very close to our minimum dimensions, and we just weren't comfortable saying they were necessarily suitable for use. Kind of the first big take-home message here is that, at least what we found in our study, when you see a potentially suitable cavity from the ground, the entrance looks like it might be the correct size. The vast majority of those cavities are not actually suitable for use, at least for wood ducks, just because interior dimensions might not meet the criteria that they require for nesting. So from here on out, for the rest of the presentation, I'm going to kind of key in on just this component of suitable cavities. In terms of the source of these cavities, the most common was from broken limbs, which is nearly 40%. And there's a few examples here of what those look like. Next most common was from splits and frost cracks, which I saw Michael had in his presentation on the aspen. It looked like a split. Again, a couple examples here. After that, we had broken tops, which come for 18%. So people unfamiliar with this, when a tree breaks off, it could rot and decay down and create a cavity, or maybe there already was hardwood rot and it broke off at that point to leave kind of a vertical entrance cavity that could be used. And then the last component, last major component was from woodpecker excavation, which was 16%. The vast majority of these are pileated woodpecker excavated cavities to meet the requirements of wood ducks. We'll kind of switch gears here a little bit and talk about, just briefly, one slide about our statistical analyses to address that main objective that I was talking about earlier, which is to identify forest attribute factors that might affect the likelihood that a given tree has actually developed a suitable cavity. And we wanted our results to be most applicable to as many regions and forest inventory data sets, so we tried to stick with basic forest attributes that are available in most inventory data sets, like FIA. So we use 3 tree level attributes, DVH, health status and species that I mentioned earlier, and 2 stand level attributes, stand age and site index. With those, well, I'll mention they're all continuous with the exception of health status, the 3 levels I mentioned, and then the 7 species of trees that I mentioned earlier. With those variables, we developed 15 different models that had different combinations, interactions, used logistic regression to model the relationship between whether a tree had a suitable cavity and those variables, selected models with AIC and cross-validation, and our top predictive model included just an additive model of the 3 tree levels variables, DBH, health status, and species as the top predictors of whether a given tree had actually developed a suitable cavity. So diving right into what those results actually look like. There's a fair amount on this graph, so hopefully I'll give you guys enough time to inspect it, but we have species on the x-axis here, so the 7 species. For each species, we have 1 bar for the 3 different health statuses. And on the y-axis, the probability of a given tree having developed a suitable cavity. Probably wondering about DBH. It's in this model. It's held at a mean value in the background just so we can inspect the effects of species and health status initially, and then I'll show the results of DBH in a second. Kind of the main obvious factors that you're probably noticing right away are that a huge effect of health status. So dead and declining trees obviously have a much higher likelihood than live healthy trees of having a suitable cavity. Not necessarily news to a lot of people here, but very interesting to see the quantitative data behind it and how dramatically different it is. In addition to that, a huge spectrum across the species, with paper birch at the very low end and sugar maple and basswood on the high end in terms of rate of having suitable cavities. So getting a little more complicated here, adding in DBH. So we have all 3 factors in these graphs. A panel for each species of the 7 species. Now we have DBH on the x-axis from about 20 centimeters to 80 centimeters, so 8 inches, so kind of a moderate-sized tree, all the way up to 80 centimeters, which is obviously a very large tree, 30-plus inch tree. Again, probability of suitable cavity on the y-axis, and now for each panel we have a line for the health status for each species. So obviously DBH, huge, dramatic, positive effect of DBH. Again, unlikely it's a surprise to any of you, but very interesting to see just how dramatic that increase is along the continuum, even for a species like paper birch that was on the lower end of likelihood of having a suitable cavity. So same effect across species. One thing I did want to give an example of was just to give you an idea, if you haven't been able to notice yet, kind of the prevalence rate. So sugar maple, that's about 60 centimeters, so 25 inches, that's dead, has almost a 50% rate of having a suitable cavity, which is really high on a per tree basis. Compare that to paper birch, 60 centimeters, that's dead. Obviously a very large paper birch that are pretty uncommon out there would only have about a 10% chance, and a live healthy paper birch that's that big, essentially a 0% chance. So kind of what I'm circling around is it's important to remember that some of these, this model isn't really accounting for how common any of these attributes are across the landscape. So our mean DBH was here, so we know out here on this end of the spectrum, these trees are extremely rare, at least in our data set, and very likely across the landscape. In terms of species, we know maybe sugar maple and basswood are probably, in terms of stem density, much less common than quaking aspen, for example. And then finally, health status, obviously dead trees, which maybe they have a really high likelihood of having suitable cavities, are certainly less common than healthy trees. So really, where the rubber meets the road is when we actually take these data and apply them to forest inventory data sets or forest management decisions. So I'm just going to end the presentation with a few ideas of how to do that and how we're planning on doing it in the future. So the first most obvious way is to take some of this quantitative data and actually apply it to stand level forest management decisions on the ground. So things like harvest types, leave trees, other harvest considerations. So to give an example, if a stand had large basswood or sugar maple, and one of the goals was to retain cavities for large secondary nesting animals like wood ducks, maybe retaining some of those large trees as leaf trees or patches would be important as they have a high likelihood of having cavities. In addition, we're hoping that our results could maybe be used at a somewhat broader scale, maybe in forest planning or harvest guidelines. An example of that is maybe with the Minnesota Forest Resources Council site level guidelines. I saw there was a talk later today about that, but there's some great information in there about cavities, mostly qualitative in nature though, and so we're hoping that our kind of more explicit quantitative measure of when cavities are developing along a DBH continuum in specific trees could maybe be more heavily utilized in some of those planning or guideline documents. And then finally, we have two ongoing analyses that I will hopefully have time in the future to talk about, but not today, that are looking at getting a much better idea of the spatial and temporal components of cavity availability. And the first is using FIA data, which we're actually taking that quantitative model that we developed, applying it to FIA data, so leveraging that. As FIA does collect data on DBH, tree species, and health status, we're able to make predictions across the landscape and across time about the number of potential cavity trees that are out there. We're just starting to get results in about that, so in the future, hopefully, we'll be able to come back and talk about that. And then, in terms of the spatial end of the spectrum, we're using a highly detailed LiDAR data set that's available in Cass County to actually model with our forest plot and cavity data at a detailed spatial scale the presence or absence of cavities. So right now, we're kind of working at about a 40-meter pixel scale, determining whether an actual location has a cavity or not. Also preliminary, so look for that in the future. With that, I guess I do have a few minutes for questions. I wanted to point out our partners here as well. Yeah.
Is there a maximum distance from water?
Yeah, it's been recognized that probably anything over about a kilometer or a kilometer and a half is probably on the far end of the spectrum or too far from water for a wood duck to nest. In our study area, nothing is that far from water, essentially. In other parts of the country where wood ducks nest, it certainly is a consideration, especially floodplain areas, things of that sort. You might want to factor that in, but in our study area, it's likely not an issue. They will readily nest very far from water. Yep.
So, I feel like I'm getting a somewhat different message from you than I am from Michael Joyce on the relative importance of quaking acid and large trees.
Yep.
Can you reconcile this for me?
Yeah, certainly. Michael.
Can you repeat the question, please?
Yeah, so the question was about quaking aspen and some of the information that Michael was pointing out that Fisher, and I don't know if you mentioned Martin as well, are really relying on quaking aspen for their cavity use in large quaking aspen. And we were actually talking about that a little bit earlier today. I think it really comes down to what I was mentioning a couple slides ago, which is the prevalence of the trees across the landscape. I don't think we haven't explicitly done the research yet, but there's not a high reason to believe that Fisher or wood ducks are selecting quaking aspen to nest in because it's better than sugar maple. If the cavity meets the minimum requirements or meets their needs and is another local habitat needs, they will likely use those. It's likely related to the fact that quaking aspen is so common across the landscape. So that's kind of also what I was getting at with when we actually apply these data across the landscape. The quaking aspen is all that's available, and we want to retain cavities for large secondary animals. That's what we have to work with, and it obviously does work for a lot of species.
And did you say that your model is blind prevalent?
Here it is, yep. But when we apply it to something like FIA, like we're doing with Mark Nelson, then it becomes much more explicit to what's occurring across the landscape. Does that answer?
It does.
Okay. Yeah.
Yeah, with regards to the site level guideline monitoring program, what factors would you like to see monitored or reported
In terms of recording data?
Yeah.
So I guess what I was more indicating is. Okay, so yeah, sorry. So the question was about the site level guidelines, and I had mentioned that it would be interesting to take some of our data and actually incorporate it into some of the guidelines. And the question was about how could we monitor that better? And I haven't really thought a lot about that. I guess I was more indicating in terms of when you look at the guidelines, there's a lot of qualitative information about where some of these habitat components are developing in terms of snags, and there's some information about cavities that's really good. But what we're trying to fill in is a little bit more of the gap on the quantitative end of the spectrum, where in this species, at this size class, it has this likelihood of having a cavity, which could give someone that's on the ground doing harvest, you know, if one of the goals is to retain cavities, they could identify what's on the site, say, this is likely where cavities are gonna occur, we wanna do X, Y, Z harvest or something like that. But monitoring, yeah, I have to think about that one, we should talk, I'm sure there'd be good ways of doing that.
We can do one more quick question if there is one. All right, let's thank Ed for a great talk.